this is actually what is needed for solid-state transformers, being able to use high-voltage semiconductors in a very efficient and reliable way. I'm very happy to see that actually technology-wise we are ready today.
This is the podcast for engineers, the podcast you just have to listen to if you're interested in what's going on in the semiconductor market. I'm your host, Kelsey Markl, and today I'm joined by my colleague, Valerio Zerillo. He is the Global Application Manager for solid-state transformers and uninterruptible power supplies here at Infineon, and he brings with him more than 15 years of experience in AI data center, power infrastructure, and critical power systems. Valerio, thank you so much for being here.
Thank you, Kelsey, actually, for having me.
Okay, before we get started, the topic today is solid-state transformers. And I have to admit, I've been doing this podcast for several years now, and we haven't really talked about solid-state transformers. A few years ago, I don't even think this was a topic we were discussing so much, at least in my area. Can you just tell me a little bit about how we got here? What is the market situation driving solid-state transformers, or SST?
Yeah, SST, which is the abbreviation for solid-state transformer, is actually a relatively old application. This has been studied since decades. However, the current changes that are being put into place for the power and the energy infrastructure is asking for more and more, let's say, modern power infrastructure systems. So solid-state transformer is actually the potential evolution of the traditional transformer systems. Those large, very powerful systems that are placed outside of power substations. Those are typically very large power systems that are interfaced on the medium voltage grid, and they are the one responsible to deliver reliable power to the end applications with a myriad of the possible application ranging from EV charging to solar, wind, energy. So the reason why SST is becoming so interesting today is because we are changing a lot into the power infrastructure. So we are adding a lot more of energy storage in terms of solar, wind. We are putting more electric vehicles associated to the grid. And lately also we are putting and building larger AI data centers. So all of these requires a change in the way the power is distributed from grid to the application.
Okay, so just basically we need more energy and we have to deal with it. Okay. You mentioned a lot of interesting things there because I also know these traditional transformers outside of power substations, these big metal areas. And but what's different is then the word solid state. So you mentioned solid state's been around for decades. I didn't know anything about it. So can you tell me a little bit more about the evolution?
Yeah, absolutely. Just to give you a reference, the first patent about an electronic version of the transformer is dated, I think, 1970. And between 1980s and 1990s, there was a lot of exploration from academic groups and the universities to kind of see what could be the evolution of traditional, let's say, land frequency transformers, those large copper, aluminum-based solutions, to let them become better suited for modern power grid infrastructure. So this has been studied for nearly 50 years now, but there was one single element that was missing. The technology was not mature. So the power semiconductors that were needed to make it happen, they were just not ready. So we couldn't have the right technology in terms of semiconductor to be able to withstand the medium voltage levels, which is actually the main point of interface of transformers into the grid.
Mm-hmm. And you said now the technology is ready. So now we're at this tipping point in the market that we need to. How did we get here? What triggered this tipping point then in terms of technology?
That's very interesting. So this has been studied on one side for several decades. On the other side, from the power semiconductor industry, there were a lot of advancements in terms of technology. So we can say that now the technology to be able to build solid-state transformers is readily available and is also proven in other applications. Mm-hmm. I'm thinking about, for example, silicon carbide power switches. Those devices can handle very high voltages, which is kind of the limiting factor for the previous generation of semiconductor technology, because this is actually what is needed for solid-state transformers, being able to use high-voltage semiconductors in a very efficient and reliable way. I'm very happy to see that actually technology-wise we are ready today.
Okay, so you mentioned, so we're testing the technology, the semiconductor technology, and a lot of other applications where you need these high power situations. But have we tested SST? Are there actual working, running SST systems out there right now?
So there have been a lot, really, several prototypes being built in decades, plenty of them. What I think is very interesting today is that we are seeing the first early commercial deployments in field. Of course, we're talking about limited installation in terms of systems and also applications. But I can mention, for example, there are already pilots running in field, so in live environments, when we consider applications like EV charging or wind and solar integration with the medium voltage grid. And also, we see there is a lot of interest also to validate the same concept also for AI data centers, because that's probably another application that would benefit a lot from solid state transformer technology.
Okay, so anywhere where you need a lot of power in one location, I assume an SST could come in handy. Are there any, you mentioned there are some use cases, some pilots who, these are early movers, right, in this industry? Are we seeing anything interesting in terms of that? I think I remember, was it late last year, we had an announcement with SolarEdge about exactly this technology, right?
Yeah, you're totally right. I think there was public news. In that case, I believe the main focus for the collaboration was, was to build expertise together to be able to actually support the transition towards DC-powered AI data centers. And of course, solid-state transformers are part of this. There are lot of other early movers and other players that are playing a crucial role, because this is really a big transition moving from, let's say, traditional passive transformers to more intelligent systems that are actually the SST like electronic transformers.
Okay, so you mentioned this passive to intelligent, or I mean, mechanical, analog to electronic. Now, in SST, what are the benefits that come with this move to electronic or to intelligent?
Yeah, I would mention probably four main benefits that will differentiate the SST versus the traditional transformer solutions. I will start with efficiency. So high frequency power converters have actually proven to be very efficient, and we could even improve the efficiency of traditional power systems, medium voltage power systems. The efficiency gain that we see really is in the range of 1% or more. The number itself could look small. However, if we put this into the perspective of the amount of power that needs to be delivered with that efficiency, this really translates into millions of dollars savings just for the electricity bill, without considering all the other infrastructure requirements that still needed to let's say to manage the losses typically out of a system. So efficiency is a big one. Another big advantage I believe is really the addition of intelligent to a solid state transformer. So intelligent systems means that those SST can really manage voltage, power quality, and very importantly, they can also manage bidirectional power flow. So bidirectional power flow is the key element to the integration of distributed energy resources, which is also in turn one of the most important parts to make sure that from utility and grid side, we ensure stability at all time. Just to give you a reference, if you consider just a very big power site like one for AI data center, there are projections that those sites will actually achieve 1 gigawatt of power in the next few years. If one of those sites is disconnected from the grid for whatever reason, for example, because of voltage fluctuations, then that amount of power will be immediately removed from the grid, which in turn can cause instability. So having the possibility to integrate this with distributed energy sources will be key, and SST can enable that because of the bidirectional power flow.
Okay, and this bidirectional power flow ensures the stability and reliability of the grid. What about the power semiconductors themselves?
So on the power semiconductor side, let's say the main advantages of using the let's say the latest technology power semiconductor in solid state transformers are related to the efficiency gain. So we are using high frequency switching devices. On the other side, there is also another important advantage because of it, which is the overall size required. So we are comparing iron and copper solutions to high power high frequency power converters, the shrink in terms of volume and size is dramatic. There is a lot of reduction in terms of space required, and nearly without using any metal in the end. So these in turns actually will benefit the overall CO2 footprint. So we actually see SST as becoming a viable, sustainable solution moving forward.
Okay. Moving forward, you mentioned, but where are we now in terms of implementation? We have the early adopters, but where are we on this transition to SST?
Okay, we definitely we are into the early deployment phase. We see early adopters already piloting SST. We also see a strong pull from a few selected applications to make sure that SST are really validated in field for that applications. I will probably mention AI data centers. There is a strong pull from that application, but also let's not forget about the EV charging, medium voltage EV charging systems, and also the energy storage integration into the grid. So I think there is a strong pull from those applications in order to move to modern, let's say, systems for the medium voltage power infrastructure.
Okay, so it sounds like the benefits are pretty clear, but I guess the benefits come with their own challenges as well. So what kind of technical challenges are our customers facing when designing these systems?
Well, there are a few challenges, of course, and those are challenges that engineering teams will need to face, solve, and some of them will become actually goals for the overall SST design and implementation. Probably one of the biggest challenges is associated to the high voltage withstand. So medium power or medium voltage transformers, they have to be interfaced with the medium voltage grid. So medium voltage is relatively high voltage, so we're talking about thousands of kilovolts. And from the semiconductor devices, we need to have solutions that are well proven to be able to withstand that voltage level. So we're not talking about volts or hundreds of volts, we're talking about kilovolts. So the main challenge, I think, is in the voltage level. But I would say that, as I already mentioned, technology is already in place and has been proven being reliable to be able to support the medium voltage levels. For example, silicon carbide power switches.
Okay, is there anything in terms of reliability? You mentioned already, we've touched on this a bit, but in terms of the semiconductor technology, what are the challenges that SST customers need to consider when designing more reliable systems?
Reliability is not compromised with SST. So actually, that's a big challenge for designers because existing traditional medium voltage transformers, they are very reliable, and also the lifetime is pretty long. We're talking about dozens of years, 20 to 30 years, with limited maintenance. So they are a good representation of how a reliable system should behave over time. And solid state transformer, they need to target the same reliability level. So it's not a trivial challenge because the use of high frequency power converters plus the controls associated to it, plus also the magnetic piece that will need to be combined together to realize an SST solution. All of that needs to be as reliable as the transformer solutions that are intended to be replaced.
Mm-hmm. As with a lot of things where we're going from fully mechanical to more electronic systems, I can imagine that price is a factor as well. Price is a consideration. How are customers dealing with this price question?
That's a very good point. So it's always the trade-off because different end applications have different requirements in terms of efficiency, size or power density, and also associated to the overall system cost. I think the move on the semiconductor side towards higher higher voltage switching devices, for example, the 3.3 kilovolt silicon carbide devices, that is a game changer when it comes to overall system cost, because having devices that can work at high voltages, that allows to, in the end, simplify the bill of material, because in place of using several devices stacked together, designers can use a single device. So this simplifies the overall power conversion design, plus it allows to simplify also the control and the additional circuitry required to run those systems. So I think the system cost is definitely benefiting from the availability of those high voltage power switches.
Okay, yeah, and you mentioned one of those high voltage power switches is silicon carbide 3.3 kilovolt. And so that made me think, what else are we offering in this? And what's Infineon's role in this? Is it just providing the semiconductors? Is it something beyond that?
I think the Infineon's role is pretty wide in this application. So the goal of Infineon is actually to provide system value. And as I mentioned, because there are several different applications, designers have really different goals when it comes to efficiency, power density, overall cost, and reliability. So the role of Infineon is actually to provide a wide portfolio of solutions ranging from the power switches. So we're talking about silicon carbide, but that's not the only technology we can offer for the SST applications, to gate drivers that are associated to the power stages, but also to auxiliary functions that are anyway required for complex systems like SST. Talking about, for example, about microcontrollers, current sensors, memory, and connectivity. So the role of Infineon is really to provide a system solution to make sure that designers can really design and optimize their SST for their and the requirements for the end application.
Okay, and you mentioned silicon carbide. In terms of power semiconductors, we also offer, of course, silicon offerings, GaN. What is the preferred technology for SST or the preferred materials for semiconductors?
That's something interesting because SST, they need to be interfaced with high voltage levels, medium voltage on the input side. So because of that, the preferred technology as we see on the semiconductor side is the technology that can really support high voltages. And silicon carbide is probably the most interesting one. The reason is not just high voltage withstand, but also this comes with high efficiency. So both of them combined in the same, let's say, silicon carbide power switch, they are the main, I would say, candidate to be used for the power conversion stages into SST. Although we also have other portion of the SST systems that can benefit from the other two silicon technologies, but also GaN. For example, for silicon, there are other blocks that are used into the SST that actually where silicon can be used, and those are typically the ones that do not need high switching frequencies.
Okay, so always a combination of the right material for the right use case. Okay, before we wrap up, as I learned from you today, SST has been on a journey. It's decades long, but it seems like right now we're really picking up momentum. We talked about a tipping point earlier, and things are moving pretty fast from what I can tell. Where do you see SST as a technology, as a market evolving in the next, few years?
SST is here to stay, and actually it's not just stay, it's making sure that yearly developments that we are seeing today will, let's say, get more validation into the key applications that SST can support, and even evolving from that. For example, from market standpoint, ideally, the desire is to have solutions that can really match the medium voltage levels. This would mean that there is a need already from the market to have SST that are more compact, more efficient, and as reliable as the transformer that are replacing in terms of traditional transformers, still keeping that medium voltage connection very reliable.
Okay. And in your opinion, what's the thing you're most excited about in terms of SST?
I like to use an analogy because I see SST very similar to what happened in the information technology segment with the move from analog to digital. So there was a very significant change in the way data information is actually created, managed, and stored. And I really see SST doing the same, just at a dramatically different level, because we're not talking about information, we're talking about power. And for the first time, we're doing this on the utility grid side.
Okay, so you think SST has the potential to really modernize our grid as well?
That would be an essential element in the grid modernization for sure.
Okay. Thank you, Valerio. It's been so nice talking to you. Thank you for bearing with me and teaching me a little bit about SST.
Thank you, Kelsey.
And to our audience and to our listeners out there, if you're interested in what's going on in the semiconductor market, please stay tuned to more episodes of the Podcast for Engineers.